Hello! In today's session on machine learning using Python, we are going to learn all about support vector machines. Support vector machines are also called SVM, and SVM stands for nothing other than support vector machines. And support vector machines are these vectors that are supported. And that's about it. That's how simple support vector machines are. This is possibly the dumbest explanation of what a support vector machine is. So in today's session, let's take a look at what support vector machines are, and let's understand them in detail and understand them what one can do with them. This training is brought to you by BlobCity. Do not forget to subscribe to our channel to be notified of more such trainings by us. So, what is an SVM? SVM is a form of a classification model. And what is classification? Classification is a form of supervised machine learning. Now hang on a second. We said SVM is a form of a classification model, and classification is a form of supervised machine learning. This is getting really confusing. What is supervised machine learning? You might have this question. So to understand SVM, we need to start by understanding what is supervised machine learning. Supervised machine learning is one of the forms of machine learning. Here you take input data and you have reference output data corresponding to this input data. You use the input data and the reference output data to train your machine learning model. This model can be any model that supports supervised machine learning, including an SVM model, which is also a form of supervised machine learning. Supervised machine learning is commonly used for several use cases, one of them being handwriting recognition. Any software that does an optical character recognition or is used to digitize handwritten documents is a supervised learning model. Even algorithms that trade the stock markets are supervised learning models. Algo-based trading is predominantly supervised learning. Face detection or your authentication mechanisms using Face ID are all supervised learning. And such models can extract the key features based on training data that is provided to it. So whether it is predicting the stock markets or identifying a specific face or recognizing characters written on a piece of paper, all of this requires prior training. And for the prior training, you give the system a pre-labeled data set. So why is it called supervised? Because in the training phase, you give this labeled data set. So if you were to recognize handwritten digits, this is the kind of data set that you would provide to the model. The data set includes characters such as 0, 1, 2, 3. These are handwritten, but these are also labeled, which means you're telling the system that the first image that you see here belongs to a 0, the second image belongs to a 1, third image belongs to a number 2, and fourth image belongs to number 3. So this is the labeled data set that you're providing to your supervised learning model. Because you're providing this labeled data set, the model itself is called supervised learning. What does it mean? It means you supervise the learning of the model. Dig a bit deeper into how supervised machine learning works. It is extremely important we understand supervised machine learning very, very well in order to be able to understand support vector machines. So the first step of training a supervised machine learning model, you start with an input data. This input data is passed into the ML model, and the ML model produces an output. This output is based on the current training of the model. The current training of the model could be any random training. So when you start training a model, you simply start with any random value for the model. However, in the training phase, the output data is not really important because we are not looking at the output. What we're looking at is the actual error compared to a reference data. So the reason this is called supervised learning is because along with the input, you're also giving it the desired output. The desired output is your reference data, or you can also call it your labeled data. So based on the labels, the model can now compute how deviant it is from your input, from your expected output. So the model has an error computation mechanism which tells it what is the actual error in the output as compared to the reference output. This error that it has is fed back to a training loop. This training loop feeds back the error into the ML model, and this allows the ML model to adjust itself to try and minimize the error. When you do this process over and over again across thousands of iterations and thousands of input data points along with thousands of labels, you land up with a perfectly trained machine learning model. And this model can very well be your support vector machine model. When you use a machine learning model that is pre-trained, you pass it input data. This time there is no reference data that you pass. The input data goes into the model produces an output, and you utilize that output for your day-to-day operations. This is the simplest understanding of how any supervised machine learning model actually works, which includes the training and the actual use of the model itself. What are some of the other forms of machine learning? The other one is unsupervised machine learning. The only difference between supervised and unsupervised is in the case of unsupervised, you do not have label data. So you do not have reference data. You allow the model to learn for itself. But in this session, we're not going to cover unsupervised machine learning. Watch some of our other videos on the channel to understand a little bit more about unsupervised machine learning. Start with understanding SVMs. And we're going to start with some of the theoretical concepts and then move on to implementing an SVM model. We will do a hands-on coding session right after this explanation. And the hands-on coding will involve creating your SVM model, training your SVM model, and then using your SVM model. So let's look at a diagram to start with. And this diagram basically has a bunch of blue dots and green dots. And then we have put support vectors to split between the blue dots and the green dots. We know which dots are blue, we know which dots are green. And this is the label dataset, and this label dataset is used to train the SVM model. So over here you see the upper zone is the blue zone, the lower zone is the green zone. Now, the upper zone can also be called the positive hyperplane. The lower zone can also be called the negative hyperplane. So the positive and negative can be relative. You can call it upper hyperplane, lower hyperplane, or you can call it hyperplane 1, hyperplane 2. So that's up to you. It depends on what scale you look at it. It's not necessarily positive and negative. But what that means is anything above the hyperplane is actually supposed to be blue. Anything below the hyperplane is supposed to be green. Now, the line that you see in between, which is the solid line, is actually called the support vector. So that's where the name comes from. When you say support vector machines, the support vector is actually the solid line that you have in between. The dashed lines are not the support vectors. So what are the dashed lines? The dashed lines are actually the maximum margin. So what we are trying to do here is we are trying to do a linear SVM. And why we say linear SVM is because we're trying to fit a straight line. And the straight linear line is supposed to split between the two hyperplanes. So when we are doing the split between the hyperplanes, we land up with creating one blue zone and one green zone. Now, what we are trying to do here is the line that's in between, which is the support vector. We are trying to make sure that the support vector is so aligned that it is at the farthest point possible from all the blue dots and all the green dots. So this vector that you see here is actually at the farthest point from all of the blue and all of the green dots. And that is why it's the support vector. It's the center point. And the distance between the margins, so this is the maximum margin. So what this vector does is basically it's a maximum margin classifier. So we're trying to maximize the distance between the blue dots and the green dots. Maximum margin is not the only classification algorithm. So there are several other classification algorithms, and we will probably discuss a few of these going forward in the training. Now, however, this blue zone and green zone doesn't really make much sense. Right? What is a blue zone and what is a green zone, right? And what is this data? Like, what are we actually looking at here? So to give you an example, for example, your blue zone could be males and green zone could be females. So you might actually have a classification between a male person and a female person, right? But what do we mean by a blue zone is male and green zone is female? Let's understand this a little more in detail. The example SVM that we have seen, we've actually taken two axes. So there's an x-axis and y-axis. And these axes, if you missed the first time, you can look at them in the figure. There are these digits that are written at the bottom and the digits that are written on the left side, right? And these digits correspond to axes. Now, we can take an x-axis and a y-axis, but how do you define gender of human beings on an x-axis and a y-axis? Now, this is a big question. So creating your entire problem space for SVM models is also an essential component. And how you define this space is very, very crucial to how your SVM model will get trained and how you will use the SVM model. So here is an example of how you can actually split up gender between x and a y-axis. So in this case, we have taken the x-axis as body weight, and we have taken the y-axis as hair length. So if we compare the body weight of a person to the hair length of a person, and we plot this in a two-dimensional space, it is kind of possible that we are able to create a classification or a hyperplanes or two hyperplanes, wherein one hyperplane corresponds to males and the second hyperplane corresponds to females. Let's say the blue and green dots are our data points, and this is how they appear when we plot it on a graph. Now, we already know that the blue data points belong to males and green data points belong to females. And we know this because we have data of known males and females. We already know their gender, and we have taken their body weight and hair length and plotted it on a graph. Now, this graph is an inverse graph. So basically, the y-axis starts from 0 hair length on the top and goes to maximum hair length at the bottom. So as you go below the y-axis, the hair length increases. This is just for representation purposes. You could have split this the other way around without any issues. Now, if these were our data points and we had to train our SVM, which is the maximum margin SVM classifier, to classify between these data points, the SVM model would basically add a support vector in between these points. So the support vector in this case could be a line like this. And this line is strategically positioned so that it has the maximum distance between all of the points that are on the graph. Training the SVM model, you will most likely start with a random line. It is not possible to have a line that perfectly classifies your hyperplanes. So your line would start at just any random line, and this could be a line that's at a 45-degree angle to both the x and the y-axis. So this would be the line as an example of what it would look like when you just start with the SVM model. Now you're going to train the SVM model. So as you can see here, there are green dots that are on both sides of the line, and this is an undesirable condition. We need all dots to be on the same side of the line, and all dots of the same color, basically, to be on the same side of the line. And if we get all dots of the same color on the same side of the line, then we have achieved a proper classification. It may not always be possible to do that, and we'll look at some of these examples a little later. So when you start training your SVM classification model, in the training phase, the starting line would start changing. So across multiple iterations of training, it's going to start realigning this line, and it's going to realign it so that it has the maximum separation between all of the data points that you have. So maximum separation between the blue dots and the green dots. So it's going to try and find the middle ground that keeps all the blue dots and the green dots at a maximum distance possible across all the dots, of course, at the maximum distance possible from this line. And this line is your support vector. So your support vector essentially keeps changing based on your current error and distances, and it'll keep changing till it finally reaches your point, which is the point at which you want it to be. So maybe you started from something like this, and then it kept, over iterations of training, it kept changing, and then finally you reached your end goal, which is this. And at this point, your line is basically at maximum distance from all of the data points that you have on the graph, which means you've successfully classified males on one side and you've successfully classified females to be on the other side. And you have achieved this classification successfully. Now, moving forward, let's understand what this actually means. So if we look at the data points, it is possible that two people have the same body weight. Like you could have a male person and a female person with the same body weight. This is totally possible, right? But they are very likely to have different hair lengths. So you would land up with probably the male having shorter hair length than the female having a longer hair length. So this data in principle makes sense, right? Wherein you have actually positioned all of these data points, and you can see that the males are generally having slightly higher body weight than the females, and the females are definitely having greater hair length than the males. However, could be certain exclusions in which men could also have long hair and females could also have shorter hair. So that is a distinct possibility which is not covered in this graph as of now. For a second, let's go back to the previous example, where we had the male and the female, and both of these had the same body weight. And you had the male on top because the male had lesser hair size, and female at the bottom because the female had more hair size. And this is what you would generally expect. However, it is not necessarily true. So this data could actually be flipped around completely, right? So you could have a green dot on top instead of a blue dot, and blue dot at the bottom instead of the green dot. So you could have a female who has same body weight as the male, but has lesser hair size than the male. So the male and female are both the same body weight, but in this example, you can see that the male actually has more hair length than the female has, right? In this case, what would you do? So if you put this data on this graph, it would look like this. And you can see that you have one green dot on the wrong side and one blue dot on the wrong side, right? And this is only because in that specific condition, you had one male and one female, both of exactly the same weight, but the male had longer hair than the female, and which is a legitimate possibility. So we've landed up with a situation like this. Now the support vector that you have drawn, or the hyperplane separation that we see over here, is actually completely incorrect. So the support vector is incorrect. And we would have to reposition the support vector. But how can we reposition the support vector, which basically classifies all of these sets into two different proper classifications, right? And that is a big question mark here. So you might actually change the vector to something like this. And this gets you the maximum distance from all the blue dots and all the green dots. However, it does have one green dot on the wrong side and one blue dot on the wrong side. So these wrong dots will exist on both sides. Now this is the error in the classification. So in the previous example, when we saw a classifier like this is a 100% accurate classifier, or even like this, or even like this. These are all 100% accurate classifiers. And this is a fully trained classifier with maximum separation, but it is a 100% accurate classifier. The training is 100% accurate. However, in the next case that we saw, wherein you have these dots across the places and then you change the classifier to this, you got it as accurate as you could, but this is not a 100% accurate classifier, which means this classifier will have some error in classifying data, but it does a fairly decent job for most of the data points. In reality, you're more likely to encounter a classifier like this than a classifier which is error-free. So you will land up with a classifier that actually has few dots on the error sides. And this is the likely scenario that you will have in most cases. Having males and females on a graph like this properly segregated is a totally unlikely scenario, right? And we need to keep this in mind, that in reality there'll be errors, and how do we handle these errors is different. So there are various ways. Like in this case, we are trying to do a line-based separation, but in reality you can put a curve there. So you can put a polynomial equation to separate the classifiers. And we will look at some of these examples of how a linear-based or a polynomial-based classifier would work. So we are going to take some example data and jump into coding and actually build an SVM model and see how it works. Okay, so it is now time that we start coding. So let's open your BlobCity Cloudbook. For this session, we are providing you with a free account on BlobCity AI Cloud. And over here, you can run your Jupyter notebooks on the cloud totally free of cost. You can choose the free plan. And it's not a trial, it's a free for life plan. So follow the link in the description of this video. So if you just expand the description, you will find a link. This link will go to a Cloudbook. This is the Cloudbook link. Click on this link and then copy this Cloudbook. You must have an account on BlobCity. So if you don't have an account on BlobCity, once you open the link, please register. So I'm going to show you step-by-step instructions on how this can be done. I really encourage you to follow me through and get your Cloudbooks opened up, because now we are jumping into code, and I want you to code along with me and follow me in the coding. This is the best way to learn. The code is yours to keep at the end of the session, so you can practice with it, play around with it, change everything. There's no setup required on your computer. All you need is an account on BlobCity and a browser connected to internet. You can also follow the programming examples through an iPad device if you're connected through iPad. So to set up your CloudBook, you're basically going to follow 5 simple steps. And I've kept a countdown timer running for 5 minutes. So 5 minutes is all it's going to take to set up your CloudBooks, and that's all we really need here. So I strongly encourage you to do so because it's going to really help you follow me in the coding. And there are a lot of example code projects that you will receive, which you can also practice after the training. So step 1 is follow the link in the description of this video. Second is once you open this link, hit the Copy CloudBook button. If you are a registered user, then you can simply log in. And if you're not a registered user, then please do register. You will have to set up an account on BlobCity to access your CloudBook. You will receive an email to set up your password. So if you're not a registered user, you can just simply type your name and email. Make sure you type your email correctly. You will receive an email notification with a link where you can set up the password. And once you've set up your password, log into your BlobCity Cloud, open the link in the video again, and this time you will see a Copy CloudBook button. So I'm going to show you how this is done. So I have my account open here, right? And my account basically is already logged in. You can see I'm logged in as Sanket Sarang. And I've opened the link that's in the video description on my tab here. So you should see a page like this, which says the name of the CloudBook is Machine Learning with Python. It's a SciPy notebook, Jupyter notebook title, and it's CPU based. And you will see this Copy CloudBook button. Again, if you're not a registered user, you will see an option on top to register or log in. So I recommend you register, log in. Once you're logged in, then you hit the Copy CloudBook button. So at this point, I'm going to hit the Copy CloudBook button. I can give a name to my CloudBook. So I can say my ML CloudBook. And I can make this my first ML CloudBook if you so desire. And then you set up a password for your CloudBook. So I'm going to set up a password here. And this password is unique to your CloudBook. This is not your account password. So each and every CloudBook can have a unique password of its own. And you can share this password with other users along with the link of your CloudBook. So this is the security measure. If you do forget the password of your CloudBook, unfortunately, there is no way for us to restore it. So I strongly recommend you remember the password or write it down or save it in your browser or somewhere and keep. So once I've given a name to my CloudBook and I've hit a password for my CloudBook, I'm actually going to type this again just to be sure. And I can hit the Copy CloudBook button. So when you hit the Copy CloudBook button, you will see a progress bar on top. It should now copy the CloudBook for me. And you can see I have my first CloudBook copied. I have my ML CloudBook. This was created from the CloudBook that is provided to you as a reference. At this point in time, I'm going to simply hit the Open CloudBook button. And when I hit the Open CloudBook button, this will actually boot up the Jupyter notebook in the background. So it's going to start the CloudBook for me. And once it's started, it's going to show me. So you can see this is a common practice. You do land up with a pop-up blocker. So I'm going to click the icon here. So if you have a pop-up blocker on your computer, which I do have, you might also see a similar icon. You should actually allow the website to give the pop-ups. It'll open and then it comes with my login page. Now, this is the page for my CloudBook. So this is where I hit the Open CloudBook button. After it's open, it comes to this page. Here I have to enter the password not for my BlobCity account, but the password for my CloudBook. So at this point in time, I'm going to type in the password. And once I've done this, it's going to log me in and I have my CloudBook. And you can see we have a bunch of folders here. We actually have a lot of project examples provided to you. We won't be going through these, of course, but you can utilize all of these in your own study. Okay. So I'm going to give 30 more seconds or so, which we have remaining for everyone to open the CloudBooks. So if you've not followed the instructions yet, or you missed any steps, you can just refer back to the slide and you can follow the steps. The link to copy the CloudBook is inside the description of this video. So click the link on the description, and from there you can just simply copy, and it's pretty obvious on what needs to be done after that. So let's give about 15 more seconds for everyone to catch up with us. and then we'll get to coding. By now, all of you should be with me on this page. And this is what you see once you open your CloudBook. So this gives you a list of all the folders, and each of these folders have different types of models. So these are all machine learning packages given by scikit-learn. So this is all courtesy of scikit-learn. They have these examples that I've given on their website, and we have loaded these examples for you inside the CloudBook. In today's session, we're going to look at the SVM package. So we're going to go into SVM. This is the folder that we're looking at. You don't have to tick mark. I'm just ticking mark so that you can see it. And I'm going to open the folder. I'm going to go into it. And inside the folder, there are basically two files that we'll look at to start with. So let's start with the file called plot separating hyperplane.ipynb. This is the file we want to look at right now. And this is the maximum distance or maximum separation support vector example, hyperplane example. So let's open this. When you click it, it should open a new tab, and it should say we are all good, and then we are in a trusted connection, and it's all set, and we can start with looking at this. So in the maximum margin separating hyperplane, as we saw before, we're going to actually create a maximum margin between data points. Now to start with, you start with the import. So I'm going to hit the run button to actually go from the next cell. So the previous cell was highlighted in blue, and I'm going to go forward. So I'm actually going to go into the imports. Now we're going to import NumPy, matplotlib because we want to visualize the data. We're going to use matplotlib to visualize the data. We're going to use NumPy for some data related operations. Then predominantly we're using sklearn, so we are importing the SVM package, and we're using makeblobs. Makeblobs is going to be used as a data set from within the sklearn package, but makeblobs will allow us to create a data set of blobs. So, and blobs are basically data that's actually clustered, so it has certain amount of clustering inside the blobs. Keep in mind, this is not a clustering algorithm. This is actually a classification algorithm, so we know which blob is what. So we're going to run through this imports. This is pretty obvious. It's just going to simply import. It's shown me that the statement is executed. Now I want to create separable data points. And what we mean by separable data points is separable data points corresponds to data points that will generally be separable on the X and Y axis, or the two planes that we choose. Keep in mind, we don't always have to choose a two-dimensional space. We can actually choose more than two-dimensional spaces. But over here, we're taking a two-dimensional space just for simplicity of understanding. So we're going to use the function called makeblobs, and this function is going to do the job for us. So I'm going to just run this through, and I'm going to run this through as well. So as soon as I run that through, we have actually created two variables called X and Y. And these variables are as a return from the function called makeblobs. And makeblobs will return the number of samples we specified. So in this case, we have specified that we want 40 samples. So makeblobs will return 40 samples for us. We have taken two centers, and we have taken random state as 6. Now, there are several other parameters that this function takes apart from makeblobs. And this makeblobs function comes from the sklearn datasets package. So we imported it. We imported makeblobs, and then we were able to call makeblobs. Without the import, you would not obviously be able to call makeblobs. Now, the several other parameters that this function takes is, for example, n samples. So n samples, what we are using is the number of data points, and these are equally divided into clusters. So over here, we have taken 40 data points, and these 40 data points are going to be equally divided into clusters, and we still have to decide how many clusters we want. So basically, in this case, if you don't specify n samples as any value, then n samples will equal 100. So the default value for n samples is 100. Now, the second parameter that this function supports is n features, which is the number of features for each sample. So the default value is 2 features. And features essentially means the number of clusters you want to create. So in our case, as we saw so far, we took data that was male and female. So we are going to keep it at 2 features. Since we didn't specify n features as an input parameter to the function is going to default it to 2 features. And the 2 features can be male and female. But keep in mind, make blobs does not have any understanding of male and female. It does not have any understanding of data whatsoever. This is creating mathematical data points just for us to try. In real life, you would, instead of using make blobs function, you would actually take your own data and then pass it into a classification model. Now, some of the other parameters that this function covers is cluster STD. Cluster STD stands for the standard deviation of the cluster. And that is basically how far apart are the points from your cluster center. So you can also specify the center box. So the bounding box for each cluster center, when centers are generated at random, right? And basically you can actually give the bounding box for each center when you're generating random centers. And default value for this is -10 and 10. Then you can also say you want to shuffle these data points. So basically, you can shuffle the data points if you so want, or not shuffle them. That's up to you. Then random states determines the random number generation for dataset creation. So this is a configuration that's given to you. So if you don't specify any value here, you will get totally random output. But if you want to get reproducible random output, then this is the actual seed to the random number generator. So if you pass a specific seed, the sequence of random numbers that gets generated after the seed actually come to be the same sequence of random numbers across multiple iterations of the program. So if you want to see the same output as someone else, you would basically pass a specific random seed. And you can change the seed and the output will change. In our case, we have actually passed random seed as 6. We have passed centers as 2, which means center is at 2. And we've put random seeds as 6 in this case. And we will take an example of how this whole thing also looks by changing the random state or the random seed. And then the last parameter that we have is basically return centers. And return centers essentially takes a value of true and false. And if we mark it as true, it actually returns the center points of the graph. We don't really care about this, so we're not actually specified it. The default is false. In some cases for analysis, you might want the centers to be returned. In this case, we don't really care. So the returned values of this function are predominantly x and y. These are always returned. So x is the generated sample. This is a multi-dimensional space. In this case, because we didn't specify n underscore features, the default dimensions is 2. So we are getting a 2-dimensional data set in x. So x actually has data points that have 2 dimensions. And 2 dimensions could be looked at as the x coordinate and the y coordinate, for example, right? But you can have 3 dimensions, 4 dimensions, 5 dimensions. That is also possible with SVM. The second thing is the returned values also give you the y parameter. And the y is the integer labels for cluster membership of each sample. So this value has integers, but it has actually labels. So these are the labels. So if you say I want features, 2 features, then there'll be only 2 integers. And each of your x data point corresponds to a y data point. So for every data point of x, you have a corresponding y value. And y is your label. So we are going to use y for the supervised learning. So what we are saying here is y is my reference output or my target output, and x is my input. So my input needs to match my desired output, and if that desired output is matched with a reasonable level of accuracy, then I can say that my SVM model is properly trained. If they don't match within a reasonable level of accuracy, then my model is not trained. And then the last parameter that this function can return is the centers parameter. And as we saw, if you specify centers, return centers is true, then it will return centers. If you don't specify it, it will not return the centers. So this is only returned if the centers are true. Now let's run past this step, right? And at this point, it's going to create the x and y. This is just documentation. I'm going to run past it. The next logical step to do is you actually create the classifier. And in this case, we're using the svm.svc function to create the classifier. And we're going to use a linear classification model for creating the classifier, right? And we take a parameter of c, where c is set to 1000, and c is the regularization parameter. So basically, the strength of the regularization is inversely proportional to c. So regularization is a function of how regular you want your data to be. So strongly regular data will be easily possible to classify in 2 buckets. A weakly regular data will not be able to classify into buckets. So do you want data points that actually mix through each other, or do you want data points that are fairly discrete? And if you have fairly discrete data points, then you put a higher value of C. The default value of C is 1. In this case, we have actually used 1,000 value because we want a reasonably regularized data. So remember, the strength of C is inversely proportional. The strength of regularization is actually inversely proportional to the value of C that you put. And over here, keep in mind that C must strictly be positive. You cannot actually pass a negative value for C. C, in this case, must be very, very strictly positive. So at this point in time, we're just creating the classifier. And what this means is we have basically made a classifier, which is an SVM classifier. We have created this. It is not yet trained, but we have set the kernel type as linear, which means we will use a straight line to classify my data set. And my data points have to come in straight lines. And because we used n features as 2, we expect there will be only one straight line and 2 hyperplanes because I have 2 features. So I'm going to create 2 hyperplanes. So now is the time that you start training this model, right? So we just simply created a classifier. We have not yet trained it. So the next logical step is to train the model. So, or you can say fitting the model. Both are interchangeable terms. So we're going to use CLF, which is the classifier.fit. And this fit function is present inside the classifier. So on line number 4, we created CLF, which is a variable. CLF is assigned the svm.svc classifier with the specified configuration of kernel as linear and C as basically 1000. And now we are going to actually train this classifier. So in training, we do CLF.fit, and we are passing the X value. And the X value here is actually the my data. This is my X is my actual data, and Y is my labeled data, which is my known output for this data. So Y tells me which X corresponds to what particular, which falls in which bucket or should be classified as what. So I'm going to run through this step, and we can see that the step ran pretty quickly. It says SVC was run, C was set to 1000, and kernel was linear. This step can take a while on some computers because there's a lot of computation, a lot of iterations happening here. Especially if you take ultra large data points or you take multi-dimensional spaces, CLF.fit can take a very long time to execute. Now, we're using this on really powerful servers, so it kind of appeared like it did nothing. It just ran instantaneously. But there's a lot of mathematical computation that's happening in the background when we're running something like CLF.fit. Now, once we have plotted this, up to this point, we have actually trained the classifier model. And we have done with everything. So the classifier is at this point in time fully trained. And that is all the code we had to write. So we wrote some imports. And matplotlib import we have not actually used so far. So this we could have skipped. So we could have only written numpy, sklearn, svm, and we would have basically been done with just that. Actually, we could have been done without numpy for the moment. We used the function make blobs, and it created the blobs. Then we created a classifier by specifying the parameters in which we want to create the classifier. And then we trained the classifier. Now this trained classifier is ready to use, so we can actually use it wherever you want. But now in the next section, let's look at actually plotting this classifier. Now there's a lot of boilerplate code that's written here for plotting the data. I'm not actually going to go through the code because it doesn't make sense, right, to go through it. If you're familiar with matplotlib, you will actually understand what we're trying to do here for matplotlib. But just to quickly explain this, we are actually going to do scatter plots. And in the scatter plots, you can see we are actually passing the first dimension of X and the second dimension of X. So the first dimension of X will become the X value. The second dimension of X will become the Y value. So we actually, when we say colon, it means all the items in that array. And then the value of 0, which is the zeroth index in the second dimension. And this is the first index in the second dimension. So we're basically taking this X and Y data. So essentially, X has 2-dimensional data, which internally has an X and Y coordinate. And C is my target value, or the color in which I want to show this. So my color comes from Y. So I'm going to actually plot the data in certain colors on the graph. So I'm going to run through this without actually explaining all of this, because if you want to really learn how matplotlib works, you can watch some of our other videos on understanding matplotlib functions. So I'm going to run this through, and this gives me my data. And this data looks familiar because we saw an image like this in the beginning of the training session. And this image was basically produced from the same program. So congratulations, you now have an image produced that you actually saw in the training, right? And this image has blue data points and green data points. And these are random data points. These don't necessarily have to be male and female people. It could be male and female people. We took a good regularization parameter, so the data is reasonably regularized. You can see that there is no blue data point in the green region, green data point in the blue region, right? This is reasonably regularized. And you have your support vector, which is the solid line that you have in between is your support vector. And then these are your margins. So the dashed lines are actually the margins. And you can see we have few data points on the margins. So anything that falls on one side of the support vector, like the lower half of the support vector is green in color. Anything that falls on the upper half of the support vector is blue in color. So when we use this SVM model, we would basically put a random data point. We would feed in a random data point, and the model will tell us whether that random data point is blue or green, right? And it's going to tell us based on which side of the support vector it falls into. Now, if that data point does happen to fall precisely on the support vector, you could get varying output. So you can actually get random output. It might classify it as blue or green. So those are the error conditions, and there are certain error margins that will exist in any model that you make of this type. But this is essentially how an SVM works. Now, if I run this program again, I'm using a random function. So I'm actually generating random values for my x and y. So can I start from this step and I run this step again and I go right through and I say go right through, and I'm going to go right through and I'm going to plot it again, and we plotted the graph again. You can see that this graph actually came to be the same graph, right? And this is because we actually put this value of random states equals 6. We put a hard-coded value there, right? Now I can actually change the value. So I can change the value to say maybe 7. And it's just a seed to the random number generator. So when I change the value to 7 and I'm going to run this through, so you can see my data points have shifted. Now I have blue on the left side and green on the right side, and my support plane or my support vector has actually completely shifted to the middle of the graph. The angle has shifted, everything has shifted. Now, if I run this again, will it be totally random? The answer is no, because I put random states as 7. It's going to actually keep giving me this graph every single time I run it, right? So I ran it and it gave me the same graph. However, I can change this value to completely remove random states from the equation. So I can actually basically completely remove this, save my program. Now I can run it through and I want to see what comes, right? Now this is a true random number generation. So you can see we ran this and we got a totally different cluster, different support vector, different planes, 2 different planes, blue on the top left, green on the bottom right. And this program I can keep running as many times as I want, and I'll very likely get different outputs each and every time. So I'm just running this through again, and you can see it was the same program that we ran, and we got a totally different output. But in this case, the output was actually so aligned that it was not possible to fit it. So you have certain bleeding conditions that you have here, right? And we'll look at some of these in the next program that we look at. So what do we do in such scenarios wherein it's not actually possible to have a perfect separation between these vectors? So just for your reference, if you want to generate the same program that I was using, you need to use random states equals 6, and you will get the original output that we had in the presentation. So you can use random states equals 6. Now for a second, let's get back to the previous diagram we had. So we had seen in this case that we actually had misclassification, and it was not possible to put the support vector to create 2 exact hyperplanes. So no matter how we put the vector here, we will always land up having some points that are actually on the wrong side, or basically on the wrong hyperplane, right? And we're going to take a look at the coding once again, and we're going to code out such scenarios this time. So let's get back to the main screen. You can move back to the previous tab that you have on the browser. And this time we're actually going to take the file called separating hyperplanes unbalanced. So we're going to open this file. This comes after the plot separating hyperplanes. This works on the same principles, but actually uses slightly different data sets, and we're going to look at how we're going to adjust it and basically work on data that's generally unbalanced. Okay, so let's open this, and it should pop open a new tab for you, just like it did for me. And this file is called separating hyperplane for unbalanced classes, which is you have unbalanced data sets. So you have data that's really hard to kind of fit together in one specific hyperplane. as well as data that has smaller data points on one side and larger data points on the other side. So you might have in a sample that you do, you might have a bias towards, say, a specific gender. So like, let's say typically you might get more number of males than females or more number of females than males, and that itself would create unbalanced data points. Like in the previous example we saw, we had equal number of blue dots and equal number of green dots. But we also need to look at what happens if we don't have equal number of blue and green dots. So what if you don't have equal number of males and females for doing an SVM classification, right? So which is what an unbalanced class is, when you have a dominance of one class, and that one class dominance actually has a lot more data points which bleed into data points of other classes. And that's where a separation becomes very, very tricky. So let's look at this. I'm going to run through these lines. And if we go to the imports fairly remain the same. Actually, nothing has changed. These are just saying matplotlib will be inline and stuff like that. What we are basically doing here is taking the same numpys, taking the same matplotlib, taking the same SVM package from sklearn, taking the same make blobs function. We're going to use the same function even this time. Now, this time we're going to go and create the clusters. And while creating the clusters, you can see here that in this piece of code, we've actually written, in the previous case, it was just one line, right? So I have the previous one open. I'm just going to go back to it. So you can see this is all that this code was, which said x comma y equals make blobs, and in single line it fit. Here we have a little more extra configuration that we are using. And the configuration basically over here, we specify non-equal sample sizes. So we are saying we want, for feature 1, we want 1,000 samples, which is here, and for feature 2 we want 100 samples. So we're going to take 1,000 samples on one side and 100 samples on the other side, and then we're going to center these points to the precise center locations that we want. So we want sample 1 to be centered at 0, 0, and we want sample 2 to be centered at 2, 2, right? So we are precisely specifying the centers that we want, and in the previous case also we did specify the centers, and we just said 2 means 2, 2. That's where the center would be. In this case, we are specifically specifying two different centers. So we are basically saying sample 1 is 0, 0, and sample 2 is 2, 2. And then we are doing cluster standard deviation. So we are saying standard deviation of cluster 1 is 1.5. Standard deviation of cluster 2 is 0.5. Standard deviation of 0.5 is generally lesser than the standard deviation of 1.5, which means cluster 1, which is 1,000 data points, will be far more scattered than cluster 2, which is lesser data points. And we'll see how this looks on the graph very, very shortly. So over here, we use the same make blobs function. We pass n samples, but in n samples, instead of passing a single value, wherein in previous case, we actually passed a single value of 40. So we had passed n samples equals 40. In this case, we are passing an array to n samples, and we're saying n samples equals 1,000, 100, which means for two features, and I don't have to mention the number of features because features by default equals 2. So I don't have to specify how many features I want, but I'm essentially specifying different number of samples across my features. I've specified my centers, I've specified my cluster standard deviation, I specified random state as 0, and we can see how it works after changing this, but we have kept it as 0, and we have explicitly specified shuffle as false. You don't really have to do this because shuffle is by default false. So even if you don't specify, it specifies the same thing. But if you wanted to shuffle your data points, then you can specify shuffle equals true. So I'm going to run this through, and this has essentially created my data set. It has created my x and y values, and x is my actual data, y is my labels corresponding to the data. Same as before, nothing has changed. Just this data is of a slightly different nature. We have a lot more data points, and it's an unbalanced data set with 1,000 on one side and 100 on the other side, right? Now, I want to create an SVM model, so I'm going to use the svm.svc function again. I'm going to say kernel equals linear and c equal to 1.0. In the previous case, we used this specific function. We use svm.svc, kernel equals linear, c equals to 1,000. We are using the same function, kernel equals linear, c equals to 1.0, and this is basically a lesser value of c, or basically a function of how much regularization we want in the fitting. So considering that this model is now created, we created the SVM model, we're just going to run this line through, and this model is created. However, at this point in time, it is not a trained model. And let's look at some of the other options that are available. So we used kernel equals linear, but the other choices for kernels are poly, RBF, sigmoid, and pre-computed. So these are the various options. You can pass one of these 5 values into the svm.svc. And based on those 5 values that you pass, it will actually try to create a fit which is specific to you. So in case of the linear model, it basically uses a linear model with a plain line that's trying to split your data across. So I'm going to run this through, and now it's trying to actually train my model. So my training function remains the same, wherein I do clf.fit x, y. Literally nothing has changed. So if I go back to the previous example, you can see here my train was the same clf.fit, but we had used a c value of 1000. In this case, we are using a c value of 1. And I'm going to run this through, and it's going to print to me svc kernel is linear. It did not print the c value because 1 is the default value. So if you explicitly specify a c value, it will print it. Because we are using the default value, it is not actually explicitly specified what's the c value at which you're printing. Now, moving on, I'm going to go with actually doing 2 things here. I'm going to train it also with a weighted class. So in the first case, I created a variable called CLF, and the CLF has my svm.svc linear classifier with c value of 1.0. But now I'm going to do one more thing. I'm actually going to do a weighted CLF or WCLF. So I'm creating one more variable called WCLF. And in WCLF, we are again using a linear model, same svm.svc function, but we are passing this extra parameter, which is class weights. And we're saying weightage is 1:10. So how are you giving the weightage to each of the buckets? Basically, that's what you're saying here. So we're putting a 1:10 weight, which means one feature needs to have 10 times more weight than the other feature, right? And this weighing can basically have an influence on how accurate your classification really is. And we're going to look at this a little more in detail as soon as we see the output. So I'm going to run this step through for now. And the next step is clearly training my model, which is a weighted CLF model. And we have passed the same x and y. So the x and y data is the same. Both types of SVC classifiers are actually using the same data. CLF is using a non-weighted distribution. Non-weighted is also equivalent to a 1:1. So if you did this 1:1, it would be same as not specifying a weight, and which is what we did in the first case. But we're going to try with 1:10. So I'm going to run this through, and now we're going to plot the results. Again, all these lines of code basically come from matplotlib. We're doing a simple scatter plot. We're not going to go into the details of this because this is simple plotting functions. We're not actually doing anything extra here. We're simply plotting the data on the graph. So let's run through this, and we're going to look at the graphs that came. Right, the training might actually take a long time, but keep in mind that based on your computer, it could take a long time. It just runs too fast here, but with 1000 data points, it can take a long time. So you can actually see that over here we have 1000 data points of one set and 100 data points of the other set. So we have two distinct groups that we can see. But because of the standard deviation of the 1000 data points being much larger than that of the smaller data points, you can actually see that these data points have bled into. So we can see two support vectors here. One is a non-weighted support vector and the other is a weighted support vector. And we're going to look at how accurate this data is based on the weighing and the non-weighing of these support vectors. But this is an interesting output. As expected, you can, of course, change the random states value and you will get a completely different output. So I can show you this. I can actually change random states to 1. I'm going to run this through. Right, I'm going to go past it, go past all of this, and this is a different output than before. This is not the same output. This is a different output than before. You can choose to not specify anything and generate a completely random output. We started with 0, so we're going to try it with 0, and we're going to look at this data on the 0 output. So we're going to study this a little more now to really understand what this weighing thing is doing and what that weighted means. And because when we land up with unbalanced data sets, that weighing actually has significant amount of significance in how you train your classifier. Now let's look at the previous graph in a slightly expanded manner. So I've expanded the graph here, and we can see that we have the blue dots, which are the thousands in numbers, and we have the orange dots, which are in 100 number. So you have 1,000 of the blue and 100 of the orange. And we have this data bleeding over each other. So you can see the orange dots are superseding with the blue dots. So there's an overlap of the orange and the blue dots. And we took two different algorithms for actually classifying this data. So we took algorithm 1, which was the default algorithm, which is the non-weighted algorithm, or you take a weight of 1:1. And the next is the weighted algorithm, right? So what you see here is the red line is actually the weighted algorithm line, and the gray line is the non-weighted algorithm line. So if you look at these two lines that you see here, the question really is which of these lines is a right classification. Clearly, none of these are actually a right classification. None of them are right. However, one is slightly better classified than the other. So the question is which of these two is a better classification? And the answer will be the red line, the weighted one, is obviously a better classification. Why is it so? Is because it does get significant portion of the blue dots incorrectly classified, but it at least has most of the red dots correctly classified. So blue is a very, very large set. So while we can see that there are a lot of blue dots on the upper half of the red line, right? So if we take this red line, and the upper half of this red line does have significant number of blue dots, no doubt, right? But in a weighted manner, at least it's doing a good classification for all these orange dots. So while it gets a larger portion of the blue dots incorrectly classified, at least the orange are well classified. So in the previous case, you saw we put a weight of 1:10. So in case of weighted, we are actually giving a weight of 10 to the orange dots. So the orange dots get a weightage of 10, and which is why these orange dots are actually being slightly better classified than the blue dots. And blue dots come from a larger space, so they're much larger data points. So even if comparatively we see a large number of blue dots that are incorrectly classified, yet there are a lot more number of blue dots which are correctly classified, right? So we cannot forget that there is a substantially large mass of blue dots that are correctly classified. Now this is how a real data in a real scenario will look like. Right now, it is almost impossible to get data that's as clean as we saw before. Like, for example, something like this, which gives you male and female classification, is almost impossible to come by. This levels of near perfect or 100% accuracy classifications simply do not happen in practical life. So almost no amount of practical data is going to get perfectly classified like this. Theoretically, you might be able to produce data that's like this, but practically, that's not likely to happen. So practically, you're going to land up with a scenario like this, and then you, as a data scientist, is going to have to take a decision on what is to be given how much weightage, right? Now, if we didn't give weightage and we gave 1:1 weightage, you can see the gray line here. The gray line is literally going halfway past the orange dots, which means it is literally classifying half of the orange incorrectly and half of the orange correctly. Now, this is not really a desirable classification, right? So if I give weightage of 10 to my orange dots, then I come with the weighted classification line. And this line has basically shifted a little towards the bottom to create the weightage for me, right? Now, what this weightage is doing is, it is allowing me to classify majority of my orange dots on the right side, on the correct side. A few of these orange dots, the ones that you see here at the bottom, are of course still incorrectly classified, but majority of them are correctly classified. And still, majority of the blue are also correctly classified. So my weighted line is actually a better classification for this problem because my majority of the blue and my majority of the orange are now correctly classified. Had I used the default gray line, majority of the blue would be correctly classified, but only half of the orange would have been correctly classified. That's not desirable. I rather have majority of the blue and the majority of the orange correctly classified. So this level of weightage distribution is something that one has to do as a data scientist. So the reason we look at this data on graphs and we plot it on graphs is actually to get an understanding of how accurate are our support vectors. So this visual representation is allowing us to know if we have a near perfect classification or we don't have a perfect classification. And then based on where your classification plane lies or where your support vector lies, you can then start tweaking on how much weightage you want to give to each, right? And then you can distribute the weightage across these points to create these classifications. Now keep in mind, I did not have to use a linear classifier. I could have used a polynomial classifier with polynomial equations. So in case of polynomial equations, I could have created a circle around these orange dots. And I could say anything that's in the circle is treated as orange, anything outside the circle is treated as blue. Right? So that is also a valid condition when you can say I want a circle here and my circle represents orange, anything inside the circle represents orange, anything outside the circle represents blue. That is also a valid classification, by the way. So there are several number of classification models that are used. You don't really have to use a straight line classifier. You can use various polynomial equations for classifiers, sigmoid functions as classifiers. And taking all of them into consideration, you can land up creating classifiers that have far more accurate representations of your data than what you see on this graph. Because even this graph is not the best accurate data. You might have like a 3% error on the orange dots in this case, but at least a 15% error maybe on the blue dots, right? So you have a 15% error in blue classification, but maybe a 3% error in orange classification. And this happened because you gave orange dots more weightage than the blue dots. Had you not given the weightage, you would have probably had like a 8% error in the blue dots, which is the gray line. Gray line is probably at like an 8% error on the blue dots, but it's literally at a 50% error on your orange dots. And 50% error is clearly non-desirable. So having an error of 3% on the orange dots and 15% on the blue dots definitely seems better than having an 8% error on the blue but a 50% error on the orange. So that doesn't make any sense. So these are few decisions as a data scientist that you have to do, because how you set the support planes, how you configure the model makes all the difference. This is why I keep saying that a machine cannot do everything for you. It's up to the hands of the data scientist to actually configure these models the right way to get the desired output that you want. Okay, so that's all I have for today. Before you go, do not forget to like this video. You can leave your comments in the comment section below the video. And also do not forget to subscribe to our channel and hit that bell icon so that you get notified of future videos. Also, we have a special offer for you. If you're looking at becoming a data scientist, we can make you a data scientist in 90 days. As long as you know programming, you can know programming in any language of your choice. We will teach you Python and R programming and everything else you need to know to become a data scientist. This is a 90 days program specially designed to offer 80 hours of live trainings. And these are live trainings conducted by trainers live. So you get to interact with the trainer. It's a two-way communication to get all your questions answered. It comes with a 30 days, no questions asked, money back guarantee. So if you're looking to bag that career jump, if you're looking to become a data scientist, if you have that dream to become a data scientist, that dream can now be fulfilled. Enroll into the program, and in 3 months from now, you will become a data scientist. Check the description of this video for more details about this training program and how to register for the training. Thank you so much for attending the session, and I look forward to seeing you again.